Hello from Bonn in Germany. My name is Lucas Reimann, and I'm a PhD student in the RealPEP project, and I'm responsible also for the sub-project dealing with the quantitative precipitation. And my today's talk is about the identification of hydrometer mixing ratio retrievals which are suitable for dual polarimetric C-band radar observations over Germany. So the central targets of the QPF sub-project of RealPEP is firstly the improvement in short-term forecasts of quantitative precipitation by numerical weather prediction models, which is planned to be made by assimilating in combination radar reflectivities and radial winds, by assimilating pre-convective information from satellite observations, and also by assimilating dual polarimetric radar data directly via dual polarimetric radar observation operators, such as the Emborado Pol developed at the DWD, and then indirectly also, which is the focus of this talk, via pseudo-observed model state variables such as hydrometer mixing ratios. The second central target of the QPF sub-project is the achievement of a seamless prediction of quantitative precipitation from minutes to hours. And we will try to achieve this later simulating nowcasted states. The assimilation of dual polarimetric observations via hydrometer mixing ratios has advantages, namely that we can circumvent costly polarimetric forward operators, which need to run simultaneously with the NWP models. And we can circumvent difficulties due to the, for example, rather rudimentary appreciation of particle size and shape distributions in the models. Disadvantage, however, is that we need retrieval algorithms to build the bridge between the radar observations and the model space, which additionally introduce uncertainties to the assessment. In this study, we focus simply on the liquid water content, mostly observed in Germany and on the ground. And we will assess existing liquid water content algorithms for C-band radar, and we'll improve and adjust these existing relations to the German climatology by analyzing a large drop size distribution data set of the German Weather Service. Two large data sets are used. The first one is the DSD data set, counting about more than 800,000 DSDs observed by DWD, including a large variety of different rain types from all seasons. And we perform T-matrix code simulations on each of the DSDs and deriving dual polarimetric radar quantities from them. And the second data set is radar data from 7 rainfall events in the warm seasons, observed by 6 of DWD's dual polarimetric C-band radars, which we see here on the right-hand side in the figure. And we consider the 0.5 degree elevation with a range resolution of 1 kilometer. And we mask the data in order to restrict the assessment to pure rain to a cross-correlation coefficient rho HV of more than 0.95. How to assess the quality of an existing retrieval and also of a new retrieval. We do this in 2 steps. The first step is we assess the quality by its skill to follow the observed interval-wise mean logarithmic liquid water content. We call this the IML along all intervals of retrieval input variables. The IML can be seen here on the right-hand side in the figure as the green dots. We want to assess the quality of retrieval by the retrieval, how it it follows the line of the IML. And we measure this by the root mean square error between the IML dots and the curve of the retrieval. And we call this measure the RMSE IML. This measure has the advantage that it's less dependent on the statistical distribution of the data than the classical root mean square error between the actual and the retrieved liquid water content. And thus we can better quantify the quality, assess the quality along the whole range of retrieval input data. The second point we need to consider for the assessment of the quality of retrievals is how the retrieval behaves beyond the data boundaries. So the expected course of the IML beyond the data boundaries should be also well represented by the retrieval. So we develop new retrievals based on the full DSD dataset and the T-matrix code simulations performed on it. And we focus on rather low order polynomial and rational functions in order to keep the extra and also to reduce the potential for overfitting. We see here on the right-hand side quintic fit, so a fifth order polynomial function in magenta color. And we see that this also already have some problems with extrapolation beyond the data boundaries, while the quadratic fit may be showing a slightly higher root mean square or IML than the magenta fit, but showing a much better extrapolation. So we consider a new retrieval as improvement over another existing or another new one if it reduces the RMSE IML by at least 0.01, and if it shows an appropriate extrapolation beyond the data boundaries. So we continue with the retrievals with the reflectivity only based retrievals. There were two introduced in the literature, one by Green and Clark, and more recently by Carlin et al. And both were linear relationships on the logarithmic scale. They were introduced as power law relationships on the linear scale. And we see here two measures, namely the RMSE IML we discussed 2 slides before, and the root mean square error between the actual and the retrieved liquid water content. We see that the relation by Carlin et al. Is less suitable to our data. Also see by the plot on the right-hand side. We develop a new retrieval, which is optimal for our data set, namely a rational fit consisting of a linear divided by a quadratic function. Also here on the right-hand side as the red solid line. Then we come to the specific attenuation-based, the horizontal specific attenuation-based algorithms. And there's also one which was proposed by Carlin et al. Again, a linear function on the logarithmic scale. And we see on the right-hand side that this linear fit does not represent so well the IML, the curve of the IML, but our new relation, again, a rational fit, represents the curve of the IML way better. Then we come to the algorithms based on the specific differential phase. There were 3 proposed in the literature, all again linear relationships, which we see here on the right-hand side plotted. And we see that the relation by Carlin et al. Is from the existing ones, the most appropriate relation to our data set. But our relation, which we derived, describes the IML, of course, much better. So which we also see in the skill values in the table. Then there's bivariate retrieval, taking into account Z and differential reflectivity, ZTR. again, one proposed in the study of Garlin et al. And we introduce here a very similar relation, also bivariate linear relation, which yields somehow better values for our data set. We also tried more complex relations, such as bivariate polynomial equations, which in the simulated case showed considerably better results. But when applied to real world, to real radar data, we saw increased errors, which is a clear sign of an unsuitable extrapolation of the bivariate function. So here's a short summary of the newly found retrievals. We see that the retrieval based on specific attenuation is shows the lowest root mean square error and the highest correlation. We see that the bivariate relation taking into account Z and ZTR is superior to that one taking only, and we see that for the highest liquid water contents, the KDP-based relation seems to be most suitable. Now we need to evaluate our new relations with real radar data, and we follow the strategy to estimate the liquid water content from the given dual polarimetric radar observations via our new liquid water content algorithms, and compare the radar retrieved liquid water content averaged over a suitable area of the radar domain with the distrometer observed liquid water content at the locations of the distrometers. And we measure the skills by the real world, measure the skills by the root mean square error between the distrometer observed and the radar retrieved liquid water content, and the correlation coefficient and the relative standard deviation between both liquid water content data sets. Here on the right-hand side, we see the evolution of the root mean square errors for the different new retrievals with increasing area of averaging the radar data. And what we see is, what is quite interesting, is that the root mean square error decreases continuously with increasing area of averaging. And we also see that the number of comparisons to this analysis also decreases, which is due to the fact that if I increase the area of averaging, more invalid values get into the analysis. And we see here around 4.5 square kilometer that there is somehow something like a local minimum, and which might be a sign for an optimal area for the comparison of a point measurement at the ground from the distrometer with a volume radar snapshot aloft. So we take for our evaluation the area of averaging of 4.5 square kilometer and use the elevation, as mentioned before, of 0.5 degrees. And we see here on the left-hand side histograms, two-dimensional histograms of the distrometer observed liquid water content in logarithmic scale versus the radar retrieved logarithmic liquid water content on the vertical axis. And we see that the peaks of the histograms lie on the ideal diagonals. Mostly we see that for the KDP-based retrieval, there is something like a small positive bias, which does not has its origin in the we developed, but in somehow a positive bias in the KDP, which needs some investigation. But what we see is that the ZZTR-based relation indeed shows slightly better results than the reflectivity-only based relation. And what is against our expectation is that the specific attenuation and the specific differential phase based relations show worse skills than the reflectivity-based relations, which most likely, and a lot of effort has been put into this, is because there are uncertainties in the differential phase at C-band, which make the derivation of these two dual polarimetric observables very difficult. Then we also did the evaluation for different rainfall types. So as we saw on the data slide, we have stratiform events, convective events, and mixed rainfall events with stratiform and convective rainfall. And we see here that the root mean square error, that's the values we see here. For the stratiform cases, are the lowest, and for the convective case, we have the highest root mean square error values. But what is the same in each of the columns is that always the ZTR-based relation is better than the reflectivity-only based relation, and that the specific attenuation and specific differential phase-based relations are somehow worse than the reflectivity-based relations. So we also compared the liquid water content not only derived from the our new relations, but also from the existing relations. And here we see that mostly the root mean square error for our new relations indeed is better than that of the existing retrievals. With the exception of the KDP-based relation by Bringi and Chandrasekhar, showing a slightly lower root mean square error, which maybe should not be overrated, as we have this bias in the KDP, which might lead to somehow maybe confusing results here. So overall, we can say that our new relations work better than the existing ones. Yeah, and with that, I already come to the conclusion that we found, based on the large drop size distribution data set of DWD, that the existing mainly power law relationships on the linear scale are inappropriate for the C-band dual polarimetric radar observations over Germany. And we found new, more suitable relations, rational functions, and also polynomial functions. And we did an evaluation of our new relations, and we found that the ZZTR-based relations outperform the Z relation, the reflectivity-based relation, and that our specific attenuation and KDP-based relations show worse skills, which might be, of course, is the reason of a difficult derivation of A and KDP, which might be a standard problem at C-band wavelength. And we also found that our new relations outperformed existing ones mostly when applied to real radar data, with the exception of the KDP-based relation by Bringi and Chandrasekhar. But this finding should maybe not be overrated. So with this, I would like to thank you for your attention, and I'm ready to take your questions.
Okay, thank you, Lucas. And